right. So our next presenter is from Intel. So he presented for the last 2 years here about a new type of RAID Z called DRAID. So today he's going to give an update about the progress of this project. So please welcome Isaac Huang. Yeah. It's down here. Oh, it's down right here?
Yeah, you see it?
Okay, I see it, yeah. All right, here we go.
I'm sure he'll be running on ZFS on Windows soon.
With no problems whatsoever.
Yeah.
Yeah, because I actually brought 2 laptops with me just in case there's some pain we have to get over. Oh, gee. I'm sorry. So yeah, my Skype on Linux refused to share desktop with Matt for some reason, so I have to do this on Windows.
Okay, just hide this a little bit, you know. Maybe that little icon there. Oh, probably it's gonna. I think it's good enough. Okay, we're just gonna leave it like that. Otherwise, yeah,
Okay.
it's gonna be like this.
I'm sorry. Sorry, Matt. Okay. So today my talk is about DRAID. It's a new VDEV driver for ZFS. It stands for Parity Decluster RAID, and it's essentially a software RAID implementation. So I guess the first question people have about DRAID is, since we already have a great software RAID implementation, which is RAID Z, then why do we bother with something else? After all, I guess for like more than 10 years or so for ZFS, we haven't got any new VDEV driver. So RAID Z, as we all know it, it has many great features. It gets rid of the write hole problem without requiring any expensive special hardware. And it's also self-healing, and it also has this famous feature to be able to resolve an empty pool in less than a second. However, there is one big problem with RAID Z, because the resolver time can be really slow and painful. The table here comes from at least the data I gathered from the community about RAID Z pool resolver time over spinning disks. Because I'm a developer, I don't have the pleasure to play with production pools. So some of the data fields are missing. But the most important data is the speed on the rightmost column, which is measured by the write throughput of the replacement drive, which I think is a good measure for the resolver speed in general. And the actual speed can be affected by many factors, like the age of the pool, fragmentation, and the block size. But in general, we all agree that the speed can use a lot of improvement. And the new DRAID VDEV driver aims at solving this resolver problem, yet at the same time providing similar features as RAID Z. For example, the same 3 parity levels, no write hole, and it runs on just commonplace hardware, and it's self-healing as well. And before we look at the details of how DRAID works, we need to take a closer look at why resolver for RAID Z can be quite slow. And there are actually 3 major reasons for that. The first one is the RAID Z resolver process needs to scan every single block pointer in the pool in order to find where the stripes are. And we'll get to a little bit more detail on this later. And also the blocks are resolved in the order that they are found, which might not be the optimal order for the rotating disks. And currently there is some mitigation through the sequential resolver work, but it cannot completely get rid of this problem. And the second reason for slow resolver is since we are replacing a drive with a new replacement drive, the speed is limited by the write throughput of a single replacement drive. No matter how good the IOs you feed the drive, there is a hard limit there. You can't go faster than a single drive can do. And there's also a similar limit to the read throughput during the reconstruction, because when a RZ VDEV is resolvering, it needs to read from all the healthy child VDEVs and reconstruct the lost data and parity. And apparently, if you have more child drives under a RZ VDEV, there is more aggregate read throughput available to the for the reconstruction. But unfortunately, a single RZ VDEV does not scale to a large number of child drives. And for example, if you have 40 drives, you typically don't configure it as a single 40 drive RZ2 VDEV, because there's various reasons why that's not a good idea. For one thing, it would split a large block into many small IOs onto all the child drives. For example, on a single 40 drive RZ2, a 128K block would be stored as 32 4K sectors on 32 data drives, and another 2 4K sectors on the parity drive, which is certainly not a good recipe for good performance. So to summarize, there is 3 major reasons for the resolver speed: the random I/O, the write throughput, and the aggregate read throughput. And do we have any solutions or mitigations for the problems? Sorry. Yeah, this was managed by Intel. So, do we have any solutions to this problem today? And the first one, the block pointer scanning problem, there's 2 ways you can mitigate that. The first one, apparently you can try to reduce the number of block pointers in the pool by using very large blocks. But unfortunately, this comes with the price of I/O amplification. And the other way to solve the problem, to mitigate the problem, would be to increase total number of available IOPS in the pool by using narrower RZ, like 4 wide RZ1, or use lots of smaller disks or SSDs. But apparently, the cost associated with such mitigations would be higher than normal. And what's more, none of these solutions would address 2 other issues associated with RZ speed, like the single replacement drive throughput bottleneck and the limited aggregate read throughput from the from all the children VDEVs. So now let's take a look at so we have a clear understanding of why the RZ resolver can be slow. Let's look at how DRAID solves the problem. The first problem we need to look at is block pointer tree traversal. First, we need to understand why RZ need to scan the block pointers in the first place. So the graph on the left shows a 5-drive RZ1. Each column is a drive, and there is 4 blocks, ZFS blocks on the RZ1. They are in different colors. So the first thing we notice in this graph is that the RZ stripe width is actually variable. So on the first block, the yellow block, it consists of 2 4x1, 4 data by 1 parity stripes. So the stripe width for this block is 5, but the stripe width for this block is 4 and 2 here, 3 here. So apparently the resolver process needs to have this knowledge in order to rebuild lost data or parity in case of a drive failure. Imagine that if we imagine that the graph on the left is all of the same color, then there is no way to figure out where the data and the parity sectors are. And that's why, and unfortunately, such information can be only found in the block pointers. And that's the fundamental reason why resolver needs to scan every single block pointer in the tree in the pool in order to do the resolver. Now, how does DRAID solve this problem? So if we look at the first block, the blocks that span the first 2 rows, it actually looks very much like traditional RAID, where the parity and data sectors are at known positions. And it would be nice if all the blocks are like this, then we don't have this block pointer scanning problem at all. So, and if we look at the last block, there is an X at the end, which is a skip sector, which basically is a padding as if the RZ adds to certain blocks for allocation purposes. And now let's imagine if we add a little bit more padding than a single sector to make every block spans a full 4x1 stripe width, then we will reach at the graph on the right, which shows the same 4 blocks on DRAID. So in this graph, first of all, apparently we use a lot more space. We use probably 25% more space than RZ1. So we will get to that point later. But for now, I think the important thing here is if we look at the graph, then we know where the priority are, where the data are, even if this graph is not shown in different colors, which means even if we don't have the block pointers, we can still do the receiver without any problem. For example, if the drive B here has failed, we can simply read 5 sectors from drive A, C, D, and reconstruct the last data to a new drive. This is essentially how DRAID gets rid of the block pointer tree scanning problem, because we don't have to know where the block boundaries are. And also a nice side effect, there's 2 nice side effects of this. The first one is since we don't have to scan the block pointers, we can just scan the VDEF from the beginning to the end, in totally sequential order, because we are not limited by the order the blocks are found during the tree traversal. And the other thing, as we just talked about, in this case, we don't have to read 2 blocks here to reconstruct 2 blocks here, and then read 1, reconstruct 1. We can just read 5 on each drive and reconstruct the 5 and write them to a single, to a replacement drive. So essentially, we get a sequential mechanism that also generates larger IOs. So to summarize, we get rid of the block pointer tree traversal problem by inflating the allocated size of the blocks a little bit. And this gives us a completely sequential, and from this point on, I'll call this mechanism rebuild, because there's apparently lots of difference between this and the RZ receiver. So this gives us a completely rebuild mechanism, just like a traditional RAID, where we can just rebuild from the beginning to the end in completely sequential order. But then, and since we are part of ZFS, we can apparently do better than just act like a traditional RAID where you rebuild from the beginning to the end. And RZ receiver can skip the free space because it scans block pointers, and there is no block pointer pointing to free space. So, but we just decided that we don't want to scan the block pointers. But fortunately, we don't have to scan the block pointers just to find out where the free space are. And we can do this by simply scanning the space map objects, which is a whole lot less metadata to scan than every single block pointers in the pool. And thanks to a previous slide, previous talk, I don't have to explain what a space map is. So basically, also this process generates large I/O because we are not limited by the block boundaries. So we have a rebuild mechanism that is like traditional RAID, which is completely sequential, but also not like traditional RAID because we can skip the free space. And so this essentially solves the block pointer tree traversal problem. But then I think one of the features that make RZ stand out among our software RAID implementation is that it does not have the write hole. It does not require any special hardware. And RZ solves this problem by getting rid of partial stripe write by implementing variable stripe width, which is a consequence of that is that the receiver will have to scan the block pointers. But DRAID solves this in a similar way, because we still in DRAID there's still no partial stripe write even though we have a fixed stripe width, because we always round up the allocation size to full stripes. So now we solve the first problem, the block pointer tree scanning. But there is still 2 other problems with rebuild speed: the single replacement drive bottleneck, and the fact that a RISC VDEV does not scale to a large number of child drives, and therefore the aggregated read throughput is not scalable. So DRAID solves this problem, solves the two problems, the read and write throughput bottlenecks, by using a mechanism called priority declustering. So there's lots of complexities in this mechanism, but today we'll just illustrate the high-level idea by using an example of 11 drives. So if we have 11 drives, we can, in the RISC way, we can configure them as two 5-drive RISC-1 VDEVs plus one hotspare, and the numbers in each block are the drive number. So here, every single column is a physical drive, so they have the same number. But just for the ease of comparison, I put a single number in every single block. So in this graph, it's clear that if we have a drive failure, for example, if drive 0 has failed, we're going to read from drive 1 to 4 to reconstruct the lost data and priority, and that is going to be written into the hotspare drive 10. So it's clear that the throughput is limited by the single drive write throughput and the 4-drive aggregated read throughput. And also, we have 11 drives, so after one drive failure, we actually have 10 healthy drives. But here we're only utilizing 5 of them to do the resolver I/O, so half of the healthy hardware resources is not in use at all. So now if we look at every row in this graph, every row is actually a permutation of blocks from 11 drives. But since in this case every column is a physical drive, so every row is actually using a same permutation of the blocks. So the declustering process, which essentially shuffles the permutations in a certain way, but at the same time keeping the priority groups and the spare position at the fixed locations at the same columns. So if we shuffle the blocks in each drive, we will end up with the graph on the right, which is a DRAID 1. So it'll be easier if we look at the spare at first. So if we look at the spare, it is no longer a single physical drive. It consists of blocks from all the drives in the pool. So it's easy to see that if we replace blocks from a failed drive and write them into this logical spare, we will distribute the write workload on all the drives instead of a single drive. So now let's take a closer look at the read. If drive 0 has failed again, if we look at the first row, drive 0 is a spare block, so there's nothing to do there. We don't have to do any work at all. And also, by the way, a side effect of having a logical spare here is that during normal I/O, we don't have any drive sitting there idle, doing nothing at all. So if we look at the first row, we don't have to do anything because drive 0 is a spare block that is not used. And if we proceed to the second row, we can see that we're going to read from drive 3, 9, 8, 7, and write the last block here into drive 1. So if we move on to the next row, it's clear that we are reading from a different set of drives. So if we go row by row, go all the way down, we can see that we are actually distributing both the read and write workload to all the drives. But the key point is that we need to distribute the load evenly, as nearly equally as possible to all the drives, so that there is no hotspot to slow down the whole process. And we can easily figure that out by, in this case, by simply going through every single row and count the number of times each drive is written to and read from. And that way we will have an idea about the rebuild I/O distribution. So we're going to skip the actual counting here and go to the actual results. So if we look at the table on the bottom shows the rebuild I/O distribution for all the drives. The first row shows the number of times each drive is read from. The second row shows the write. So clearly we are distributing the rebuild workload equally among all the drives. And there is actually two very important things that this table does not show. The first thing is that this table comes from the rebuild IO distribution after drive 0 has failed. But it's important to know that regardless of which drive has failed, we are going to come to about the same results. That is, regardless of the actual drive failure, the rebuild IO distribution is going to be the same. And the other thing is also we are using only 11 drives here. This mechanism actually scales to a much larger number of drives because due to the limit of space, I can't easily show a 90 drive example here. So to summarize, we solve the read and write throughput bottleneck problems by distributing the read and write workload among all the drives instead of just the drives that belong to a single redundancy group. And also, if we move back, so from here we can also see that each priority group consists of 1 priority plus 4 data, but at the same time the DRAID VDEV has 11 drives. So DRAID essentially decouples the redundancy group size from the number of child drives. This is unlike RAID. For RAID, if you configure a 11 drive RAID 1, you are going to get 10. You're going to get 10 data drives and 1 priority drive redundancy group configuration. But DRAID completely separates the two, decouples the two. That's how DRAID can scale to a large number of drives without splitting a very large block into too many drives. So far everything looks pretty good on paper. So I'm going to do a live demo on real hardware using the current code. So I'm going to do a demo with 43 drive DRAID 2. It's configured as 4 redundancy groups. Each group has 8 data drives and 2 priority drives, and there's 3 distributed spares. And we are going to, the pool is very lightly used because I have to squeeze this demo into this talk. And each drive is capable of doing about 150 megabyte per second I/O. So this is an important figure we are going to need in just a little bit. So here I'm going to take 1 drive offline and rebuild it to the distributed spare and see the results here. Oops, sorry, this add from. Okay, sorry. Oh, Matt is here again.
Matt is everywhere.
So this is the zpool status. So we have a DRAID 2 double priority, but unfortunately this currently we can't see the number of data drives in a single priority group because the pool doesn't the command doesn't show that yet. So we have 43 drives. They all belong to a single VDAV. And I think the interesting part here is the spares. We have 3 spares, but they don't point to any physical drive because they are they consist of blocks that comes from all the 43 drives. Now before I start the actual rebuild, so I'm going to use this tool to show the read and write throughput of all the drives. So this is a live I/O visualization. The graph on the top shows the read throughput in megabyte per second for all the 33 drives in individual lines, and the bottom graph shows the write throughput of all the individual drives. So currently there is nothing going on yet. So now I'm going to offline 1 drive, SD. Now I'm going to replace it. But instead of replacing it with another physical drive, I'm replacing the offline drive with a distributed spare, which is essentially blocks from all the drives. Now if we go back to the graph. So we can see that from the top graph that all the drives are actually doing reads. So the load is not perfectly equal among all the drives. We'll talk about that in just a little bit. And the bottom graph shows the load on the right. So basically, all the drives are doing write. So also the write throughput looks a little bit low. It's kind of like under 20 megabyte per second. But keep in mind that there's 42 healthy drives doing the write. So it's not a single drive writing at 20 megabyte per second. So we can see that the rebuild has actually completed. So if we go back and take a look at the pool status again. So the first thing we can see here is we have rebuilt so about 17 gig, which is the amount of data and parity that is written to the distributed spare in 37 seconds. And actually I had to patch the zpool tool because by default it does not show seconds. So here we can see that the offline SD device has been replaced by a distributed spare. And if we go down, we will see that the spare is now in use. So basically it acts just like a normal spare, except that you can only use it to replace a drive in its parent DRAID video and not anything else. So now let's go back to the slide. Oops, sorry. So we have shown that the rebuild completed in 33 seconds. That means the aggregate throughput is over 4 gigabyte per second for read. So that's apparently much larger than any 10 drives can do. Because if this were RAID, only 9 drives would be doing the read instead of 42. And what's more interesting is actually the write throughput. The aggregate write throughput for the rebuild process is actually for nearly 500 megabyte per second. As this is a very important figure because we said before that a single drive can do about 150 megabyte per second at most. So we have these 43 drives. So it would be great if we can do a comparison by configuring the same 43 drives as 4 RAID2 VDEVs. Each one has 10 drives and 3 hot spares, and put the same data on the pool and compare the speed. So unfortunately, we don't have the time to do that today, but fortunately, we don't have to because we know that RAID resolver is going to write the last data and parity into a single drive, which can do at most 150 megabyte per second. So even if it is able to do resolver at that speed, we are still at least 3 times faster. But what is not shown here is that this mechanism actually scales to more drives. So say if we have 83 drives, if we configure them similarly, the read and write workload is going to still be evenly distributed to all the drives. So, but if you do the same thing with RAID, if you configure it as 10 drive RAID2, the speed is still limited by a single drive. So this process is not only faster than RAID resolver, but it also scales to a much larger number of drives. So the last figure we can of interest here is the combined read-write throughput of a single drive, which is 115 meg, and this is lower than what the drive is capable of doing, which is about 150. And the main reason for that is that this pool is only 2% full. So due to the nature of parity declustering, when you have so many drives but you have so little data, it's kind of hard to distribute the load to all the drives completely equally. So that's why we are not. So during the process, we'll see that some drives are actually goes slightly faster. Some will go a little bit slower. That's why that's what brings down the average combined throughput for each drive. But that's not a problem once you have a pool that is at least 10% full. So now, so far, I've been painting a very rosy picture of DRAID, right? So it offers the same features, the same parity levels as RAID. No write hole, runs on special, does not require special hardware, And at the same time, it has a fast scalable mechanism to rebuild. And it's free software, so you guys don't have to pay us a dime to use it. But there is some cost to consider. The first one we have seen previously, apparently there is space inflation. As far as this graph shows, we are using 25% more space than RZ. And so when we compare the space inflation, the first thing we need to keep in mind is that we are comparing DRAID to RZ because we're offering similar functions. We're not comparing DRAID inflation to zero inflation. So if we look at the block, the green block here, although DRAID adds 2 sectors or paddings here, RZ also adds 1. So DRAID actually introduced 1 addition. So from this graph, it's very clear that if your workload, if your data consists of many very small blocks, the cost is going to be very, very high, the cost of inflation. But on the other hand, if you have mostly larger blocks, then the costs get amortized a little bit. So it will not look this terrible. And now we should look at 2 special cases. So the first special case is the first block. We can see here that this block does not use any padding at all. This is because we only need to pad up the physical size of the block to a multiple of D sectors, where D is the number of data drives in a redundancy group. In this case, if we assume 4K sectors, we only need to pad up the size up to 16K. So if you do not use compression, the ZFS logical block size is the same as physical block size, and which is always a power of 2. So if that is the case, then that would be a perfect workload for DRAID, because any block 16K or larger will require 0 padding. So there's 0 inflation for such blocks. And then if we go ahead and look at this block, the gray block, apparently this is the worst case, because this is a single sector block, and we add 3 sectors of paddings to it. And also, if we look at the whole picture, DRAID adds 6 paddings, 6 sectors of paddings, but this block alone adds 3 sectors. So if we can somehow mitigate this special case, this worst case here, if we can get rid of paddings for this block, we're going to cut the inflation by half, as far as this graph shows. And that's exactly what DRAID does. So in DRAID, and thanks to a previous talk, I don't have to explain this metaslab, okay. So most of the metaslabs in DRAID are actually exactly like the graph we show on the left, which is parity plus data. But there's some metaslabs we configure them as mirrors, so that for this worst case block, instead of saving this block as P0, D0 plus 3 sectors, we actually save them in a different place, in a different metaslab. And we save them as D0, D0 twice. So we cut this, we totally get rid of the space inflation for this case. And for this graph, we cut the inflation by half. And also for write, we don't have to compute the P0. And for read, we can read from either copy of the D0, so we get better IOPS for read. So to summarize the block size inflation problem, it doesn't work well with small blocks, but we have a mitigation to address the worst case scenario by using mirrored metaslabs. And there is also other costs that users need to consider. The first one is, since we do not scan the block pointers, and the block checksum is part of the block pointers, so there's no way we can verify the block checksum during the rebuild process. So after the rebuild, users would still need to verify the checksums, for example, by scrubbing the pool. But the point is that we quickly and in a very short amount of time restore the redundancy. So if there's any further drive failure during the long scrubbing process that does not affect the pool, we're not going to lose any data. And also the parity group and spare capacity is chosen when the VDAV is created. So for example, this one is A by 2, 4. There's 4 parity groups, and once the pool is created, you cannot change that. And also, in addition to that, the spares, apparently they are part of the DRAID VDAV. They are not the traditional house spare where you can share it among different top-level VDAVs, and you can even share the traditional spares among different pools. But the DRAID special pool can only be used to replace any drive in the parent DRAID VDAV. So those are the limitations. And so the current project status. So the code is the project is mostly, I think, feature complete. The code has been pushed on GitHub for a while. So this code is actually a little bit outdated because we are waiting for the metadata allocation class to merge first, because we need that feature to manage our special mirrored meta slabs. So once that feature is merged to ZFS on Linux, I'll be able to refresh this pull request with latest code. And I have the document here on GitHub as well, and I always try to keep it updated every time I update this code. And of course, we need a lot of help from the community to review this code, testing, patching, and even porting it to other operating systems. And by the way, currently we only have this on ZFS on Linux. So now I can take questions. Please.
So, first, very cool. But one of the other difficulties with RAID-Z is this random read performance. Does DRAID make any improvements on random read performance?
Well, if it's a block that is mirrored instead of, oh, sorry, the question was because RAID-Z has this problem of random read performance. And does DRAID do anything to improve that? I think one way DRAID improves that is we store the smaller blocks on mirrors rather than as a normal RAID-Z. So that way we can read from user copies. So we get better IOPS from there. So basically, we can just imagine that as small blocks are simply mirrored. So it acts more, for smaller blocks, it acts more like a mirror than RAID-Z. For Linux version, probably not yet.
I think that was never open source.
Yeah. Oh, really? Yeah. Did Jeff do that work?
Yes, but it was open source. But even so, that actually addresses only a very small subset of the cases that this does, because the hybrid mirror stuff that is in Oracle ZFS, like it only it's only if you have like a very small number of sectors that you can do that, because of the need to allocate full stripes.
Sure.
Versus this, you can say like, oh, I have like a 4K drive and I want all my blocks that are less than 32K to go into this mirror mode, even if they're multiple sectors.
Okay, so that wasn't clear. So this actually has the ability to use to not just a single sector ones, but
Right.
so you can so that's a setting you can tweak to say which size blocks you want to talk about. All right, that makes sense.
So I think it's only single sectors.
In hybrid. Hybrid was, I think it wasn't single, but it was a very limited set.
I think it's like less than a full stripe.
Yes.
Essentially.
Any question? Yes. Yes, please.
Okay, cool. I have 3 questions really. First of all, you said that any block size above 16K adds no padding. That, from at least the way I understood it, that doesn't really make sense to me. Maybe I didn't understand it right, because it would seem that basically the problem is anything that does not divide to an even multiple of stripe width times allocation unit size.
Right. So by that I mean if you don't use compression, because without compression the logical block sizes are power of 2.
Even without compression, you get right short. Even without compression, you get without compression, you yes, with compression it gets any multiple circuit is exactly 48.
No, I understand that. It is example this, but I mean, I think the point is that depending on the stripe width, you can run this problem without.
Yeah, I think Isaac's point was qualified by if you're not using compression and if you're using this layout of
Yeah,
data
this
file.
particular one, because
So yeah, like in general.
yeah, that's not a general conclusion. So if we generalize it a little bit, if you configure the number of data drives in a priority group to be a power of 2, and if your sector size is of course power of 2, then any block that is size D multiplied by sectors and larger without compression is not going to require any padding, any inflation at all.
And if it's not, then like on average, you're probably going to have padding of like half of one stripe per block, right? Yeah.
Right.
So
Right.
you know, if the stripe is 4 sectors wide, then on average you're wasting two sectors per block. So if you have like 128K blocks, and then if you press down, you're wasting like 16K per each. Maybe it's 10%.
So the most number of paddings we're at is actually deep -1 sectors for each block.
So like on average, you might, in this example, you might waste 2 on average if you have random block sizes.
Right. Right.
My other question, I guess, well, we can roll those into one, so make it one question, is how does this interact with having different drive sizes in the pool? For instance, is it possible to still grow a DRAID VDEV by replacing all the drives?
I think technically, the question was can we grow a DRAID VDEV by replacing each drive with a larger drive?
Possible to make some, for instance, like I have a 1 and 2 terabyte drive, or a couple like that don't align exactly, like have
Yes.
2 terabyte drives that don't have the same firmware, they don't have the exact same sector count.
Yeah. So basically, but the question was if I replace all the drives in DRAID VDEV, then can I essentially increase the size of the DRAID top level VDEV? The answer is yes, but you have to wait for all the drives to be replaced to actually see the space increase.
Same as RAID.
Yeah. Yeah, it's basically just a VDEV driver.
So a couple questions. One is, when you look at the Z-pool status, does that show the actual parity group geometry? Is there a way to see what the geometry is for that top level?
Currently it does not. But yeah, there is a command to see the config, because basically we save the configuration file somewhere. And by the way, this interface is probably going to change. But the short answer is we will provide something to see that. For example, in this case, the pool was created from this configuration file, which contains the permutations we use. So if we look at this one, the contents. But by the way, this is also saved on the disk levels on all the drives. So we can see that there is 4 parity groups. Each one has 8 data drives, and there's 3 distributed spare. So yes, well, this interface may change in the future, but yes, there's going to be something to show you that.
And then the second question is, based on your testing, have you kind of found what is like the sweet spot, or does that really just depend on what your block size workload is going to be, as far as like the actual parity group size?
So the question was, is there a sweet spot for the configuration for the rebuild performance? And yeah, we haven't done too much performance testing yet. But at least in theory, because since we are scanning the space maps, we are less impacted by like fragmentation, or because we are scanning the allocated segments instead of doing the blocks. So yeah, of course, there's going to be some impact if there's lots of fragmentation in the space map.
I think that the fundamental trade-off is similar to what you have when you're configuring your Z today, right? Like how many, like what's the stripe width and how many bases do I have? Kind of the same consideration. It's fundamentally how I think the parameters will work out better here.
So currently, resilver and scrub use essentially the same syntax with like just a couple of if statements making them different. This would completely, I'm assuming, rewrite resilvers.
It does not rewrite resilver. It's a completely new code. So it's a new process.
But would that render the current resilver? Well, I mean, I guess the current resilver code would always be used for RAID Z or JBOD or anything else like that. But if for RAID Z would never run the current resilver code. It would always run RAID Z or the DRAID.
Yes.
You still have to run the scrub.
Yeah, that was my second question. Is so after I've done a resilver, I now have to run a scrub, which will have to traverse all the block pointers. So I've gotten back to like my parity level, but I'm not sure that any of that's correct for a little while until once the scrub completes. I just wanted to like that's probably a good trade-off in most cases because it gets you back to probably redundant really fast, but you don't know that it's
Yes, but the thing is we don't override anything that is already there. So the only time where this rebuild process can generate data that does not match the checksum would be where either one of the drives silently returned corrupted data to us, or if the data we write to disk somehow get corrupted. So that's the only case. And yes, so you will know it when you scrub it or when you actually read the block, because that's where the block pointers are verified. Oh, sorry. Okay. So basically the question was because this rebuild process does not verify the checksum, so we still need to scan the block pointer tree in order to verify the block integrity, and the answer is yes. And spare. If we use this as an example, so if this is single priority, for example, we failed one drive, replaced it with distributed spare without adding any new hardware, without adding any new drive to it, and if during the subsequent scrubbing process another drive fails, so at that point we have failed two drives, but we would still have the full redundancy. We would still be able to issue IO because the first last redundancy was rebuilt to the blocks on the other drives already. So, yeah.
You showed us what happens when you take one of the disks and replace it with a distributed spare. What happens when you want to bring that pool back up to full redundancy? Like, I want to put a new disk in to be that replacement and get rid of the distributed spare use.
Okay, so that would be exactly the same as what you would do if you have to. So basically, what you need to do is to replace this drive with a physical drive using the zpool replace command. Oh, sorry. All right. So the question was, since we have replaced this drive with a distributed spare, and a consequence of that is this distributed spare is in use currently. So what is the operation that's necessary to bring this pool to its original state? So at this point, what you can do is to replace this drive with a new drive. And that process is going, and by the way, that process is going to use the actual resolver process. So that, and after the resolver is done, this spare space is going to be available again. And so if you have rebuilt a DRAID VDAV to a distributed spare, and if you have plans to like immediately replace the drive, which you don't have to because we have restored all the redundancy, but if you do have plans to replace the drive with a physical drive, then you don't have to scrub the pool, because during the actual drive replacement where you replace this drive with an additional drive, all the block pointer checksum is going to be verified, because that's using the resolver process.
I feel like calling it full redundancy is a little bit misleading, though, because the spares are actually part of the VDAV, and if you lose a spare, it's going to have to do a bunch of IO to make a new one.
Well, in this case, I can actually show it. Okay.
Yeah, I'm going to disagree, because you've been returned to be able to survive two drives. Like in here, you returned to be able to survive any two drives failing without losing data.
So I'm good.
Any two drives plus any free spares is the redundancy profile you're actually picking, right?
Sure. Like if what you're thinking about with DRAID Z is I can lose any two drives of my DRAID Z, and I can lose all three of my spares.
Right.
Yeah. Then it's a little different.
And actually,
Here you can never lose all three of you. Like you don't have spare devices, so you return to the full redundancy that's offered by you.
Right. You're basically making the spares part of the VDAV.
Correct.
Yeah.
Exactly.
It's rewriting those spares essentially.
Yeah.
I think the point is to like really greatly reduce the window where you're vulnerable to a total data failure, and this reduces it like many magnitudes.
Yes, exactly.
Right.
So okay.
I think we have maybe time for one more question.
Yeah. Oh yeah.
Okay, that's it.
There is one more.
There's one more. Okay. Sorry.
Can you, I mean, I feel like you're taking what we used to implement as multiple VDAVs of RAID Z and bringing those into the RAID. So would there be any point to creating multiple VDAVs in this model?
So the question was, so would there be any point in this model to create multiple DRAID VDAVs if you have a lot of drives? I think, well, if you grow your number of drives during the lifetime of the pool, for example, then since you cannot grow a DRAID VDEV, so you have to put the additional drives into a new DRAID VDEV. That's one case where apparently you have to do that. There are cases where if you have because this, so fundamentally this, so the most difficult part of this priority declassing process is to distribute the load evenly among all the drives, totally equally. Because we showed a example where there is 11 drives and read and write throughput are completely equally distributed among all the drives. But if you have over 100 drives, then it will become more and more difficult to do that. There will be some slight variance in the load. So then, in that case, it may make some sense to create two smaller DRAID VDEVs. But
in generally speaking, no. You put all your drives into the one DRAID.
Right, because generally it's like what we did with taking RAID into ZFS. Now we're taking VDEVs into RAID.
okay.